Alright, Chapter 9 is over estimating the value of a parameter, and what we're going to be doing in Chapter 9 is, what we've been doing in this course in general is looking at values, maybe taking the mean of something, say our tests. And we've just been looking at samples, and what we're going to be doing is we're going to be taking samples and we're going to be estimating those samples about the population as a whole. So, 9.1 is about population proportion. So once again, a proportion is just a percentage, a decimal, or a fraction. That's supposed to be a number. I'm just going to write an actual fraction. 3/4 or 0.75. I don't know. Alright, so here's what we're going to do. We're going to obtain a point estimate for a population proportion. Remember, population is the whole. Construct and interpret confidence intervals for population proportion. And determine the sample size necessary for estimating a population proportion. So, we're talking about proportion all today, or all in 9.1. And so, proportion, again, remember, is a percentage, fraction, or decimal. So, what is a point estimate? A point estimate can be either a proportion or a mean. And we're talking about specifically a proportion today. And it is the value of a statistic that estimates the value of a parameter. Remember, parameter basically means population. So we're going to use that point estimate to estimate our population. And so the point estimate for population proportion is p hat is x over n, where x is the number of individuals in the sample and n is the sample size. So, I don't know, let's just say we had 10 people in class, and I wanted to know how many people have brown hair. So X would be the people with brown hair, so maybe we have 8 people with brown hair out of everyone. And so that's how you get that p hat. It's pretty straightforward. So it's part over whole. What are you looking at divided by however many people you have? Here's another example for calculating a point estimate for population proportion. When you see a point estimate for population proportion, you know that it's p hat. And we also know that p hat is x over n because we were just given that. So in July of 2008, a Quinnipiac University poll asked 1,783 voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. Obtain a point estimate for a population proportion, or for the proportion of registered voters nationwide who are in favor of the death penalty. So how many people are we talking about? Well, we had 1,783 people registered. So that total amount is your N. And then we care about the people who were in favor of the death penalty. And we were given that number in favor. So that's my X. So I'm going to plug in these values. And that is my point estimate. I got 0.6298. So this is, if we were to ask, what is this? People, it doesn't say a specific place. So people who were in favor of the death penalty. This value, maybe it's not exact because we only asked 1,783 people, but it gives us a good idea of how many people are in favor of the death penalty if we did the sampling in a good way. So it's not exact, but it's likely to be pretty close to the actual Like if I were to ask everyone in the United States, maybe it's actually 0.64. Not this 0.62, but this sample, this point estimate gives me a good idea of the population as a whole. And so keeping that in mind, because I can theoretically get close to my population with a point estimate, I can do something called a confidence interval. And a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. So it's based on that number that we just found. The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted 1 minus alpha times 100%. And so, basically, it's probably going to be a little confusing just logistically right now until we do an example, but just a visual. Let's say I have my normal distribution, and let's just say my p hat goes in the middle. That's my point estimate. And my point estimate was at 0.6298. And so if I can create maybe some numbers that I add and subtract to this point estimate, kind of like a give or take, I can create something called a confidence interval. And it gives me an idea. I'm like, well, I don't know if it's exactly 0.6298, but I know it's somewhere close to that, so I could essentially create some interval, called a confidence interval, of where I think the actual population proportion exists. And so we're going to get into that a little more and calculating that, but this is just a visual of what a confidence interval is. Interpreting a confidence interval is very important when you're looking into confidence intervals. It's an important part to understand. And so what it means to interpret a confidence interval is you can have different percentages of confidence, and 95 is a very common one, but it could be different things like 90, 80, 99. It's never 100 because you have to leave a little room for error. But for a 95% level of confidence, alpha equals 0.05 or 5%. Alpha is the leftover. So if I'm 95% confident, then I'm going to leave a 5%, basically room for 5% for me to be wrong. So alpha equals 0.05 implies that if I were to create 100 different confidence intervals, then each based on a different sample from the same population, I would expect to be right 95 of those intervals, and 5 I would be wrong. So if 95 would actually include the population, it would include the parameter that we're trying to get, and 5 would not include it. Let's say I did an 80% confidence. That means that if I were to do 100 different confidence intervals, then 80, I would expect to be correct 80 of those and 20 of them to be incorrect. So as you lower your level of confidence, you also lower your expectations of getting as many correct. I do have a visual a little later to kind of help maybe understand what this is saying, if that was a little confusing. All right, so this is how you're going to create your confidence intervals. It's going to be your point estimate plus or minus your margin of error. Definitely write this down. Depending on if you're doing a proportion or a mean, which in this case we're doing a proportion, that's going to be your point estimate. So in this case it's our p hat plus or minus our margin of error. I'm just going to put MOE. So that margin of error just is a give or take, basically. It's like when you call the pizza place, let's say Domino's, and they say the pizza's going to be here in 20 minutes, give or take 5. Even though 20 is not a proportion, that's just the example I like to use. So if you know that the pizza is going to be here in 20 minutes, give or take 5 minutes, I can expect it to be here anywhere from 5 to 25 minutes because 20 minus 5 is 15 and 20 plus 5 is 25. I just created a confidence interval. And that's all it is. It's taking that point estimate and finding that give or take, that margin of error. And that's how you create that confidence interval. So, couple things on margin of error. It depends on 3 factors. The level of confidence. Remember I told you it could be different levels, say 80%, 95%. 90%. As the level of confidence increases, the margin of error also increases. Sample size. As the size of the sample increases, the margin of error decreases, which hopefully makes sense because the more samples you get, the less error you expect to have, the more legit our data is going to be. And standard deviation, the more spread there is in the population, the wider our interval. So hopefully that makes sense too. The more spread out it is, the wider the interval is going to be. So for p hat, we're going to have to do different things for sample proportion and sample mean. But this section is only sample proportion. So for sample proportion, remember that mean is just equal to the mean. And standard deviation is this long formula. And to see if it's normal, you need to do n times p times 1 minus p. It needs to be greater than or equal to 10. Alright, this slide did not format correctly. If I were you, I would go back or at least try to be following along in the blank PowerPoints, and you can see what it's supposed to look like, but I'll just write what it's supposed to look like. These are the steps of finding a confidence interval for P. So you're going to assume that a good simple random sample of size n is taken from the population. And you also need to assume that n times p hat 1 minus p hat is greater than or equal to 10. You actually need to test that and figure out if that's true. And so you'll see me doing it in all our examples. And that is just, if it doesn't tell you that it's normally distributed, you have to see if it's normal. Normal being we're basically good to go and our distribution is bell-shaped. Okay. I'm again just going to write all these steps, and I will kind of explain them as we do an example. So definitely write these down, and maybe this is even something that you would put on a note card for an exam. So set confidence level to 1 minus alpha. Confidence 1 minus alpha. Because a lot of the times it gives you alpha, but it doesn't give you the confidence level, or vice versa, so we can find either or. And remember, the alpha is the leftover. So solve for alpha. And alpha divided by 2. Find the z-score for alpha divided by 2. Plug it in the formula. which is on the next page as well, but it's p hat plus or minus z of alpha divided by 2 times the standard deviation, which is p hat times 1, the square root of p hat times 1 minus p hat, all divided by n. And your last step is to interpret. So go ahead and write that down. These are important steps, which may seem really weird right now, but we will talk about going through them. So that p hat that I just wrote down when I said p hat plus or minus all of that is your margin of error. So that's that give or take. That's that 5 minutes, the pizza, give or take 5 minutes, right? It's really pretty straightforward. The hardest part is finding the z, but I have a trick. So bear with me. But go ahead and write that down. That is the margin of error. And remember to find a confidence interval. We were told it's a point estimate plus or minus a margin of error. And so that's, again, that plus or minus. All right, so this is how we're going to construct a confidence interval for population proportion. This was the example that we used earlier in July of 2008. It's the amount of voters we asked who were in favor of the death penalty. And remember, to find p hat, we just did part out over whole. 1,123 divided by 1,783. Oh my goodness. 83, there we go. And for my p hat, I got 0.6298. Did that earlier. We're going to add something to it. Obtain a 90% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So, first things first, it doesn't tell us that this was normally distributed or approximately normal or anything like that. So we have to do this thing first. N times P times 1 minus P needs to be greater than or equal to 10. P hat, not P, sorry. If you're thinking, what's the difference between P hat and P? P hat's just the sample, and P is the population. So we're given the sample, so we're going to use P hat. And then N is the amount of people we asked, so that 1,783. 1,783 times P hat, 0.6298, times 1 minus 0.6298 needs to be greater than or equal to 10. When I put that in my calculator, I get 415, which is greater than or equal to 10. You have to do that to see if it is, you can even do a confidence interval. It has to be normal. And so that's really just kind of a logistical thing that you have to do. But once we're good to go. So I'm going to erase that. If you need to pause, go ahead and pause. So, put my P again. 0.6298. And I'm going to go through those steps. So we know that we're using a 90% confidence interval. So let's find alpha. To find alpha, it's 1 minus the confidence level as a decimal. So 1 minus 0.9 is 0.1. And let me show you what's happening right now. We're doing a 90% confidence interval. And if we're doing a 90% confidence interval, we're capturing the population proportion 90% of the time, which means that 10% of the time we're not going to capture it. And that 10% is going to be out here and out here. It's going to be on what we call the tails. And so that's why we find in step 2, we find, so if that equals my alpha, step 2 says to find alpha divided by 2. The reason we do that is because there's 2 tails. So I'm going to do that, 0.10 divided by 2, so 0.05. So there's basically 5% in each tail. The next step is the hardest part. I'm going to go ahead and erase that really quick so we can move on. And so again, my p hat, I keep erasing that part, is 0.6298. And so I just did steps 1 and 2. And step 3 says to find your z-score of alpha divided by 2, which we know is 0.05. So what you can do is you want to find the z-score that goes with this area. And we did this before, where we look up this 0.0500, technically, if you want to use it as a 4-digit decimal. And you look that up in your z-score chart, and you find the z-score that goes with it. And there's going to be 2 that's really, really close. 0.495 and 0.0505, which are the z-scores. Let's see, it's the z-scores that go with this is 1.64 and 1.65. They both are really, really close to that area. So if you average those together, it's 1.645. That's the hardest part. Now, let me tell you, if you were a little confused just now, you don't always have to do that. You don't always have to look up the area. There's a little cheat sheet. And I want you to look at your z-score chart while I'm talking to you if you can on this video. So pause and go to it if you need to. It's under course information or that resources, the very first module tab. And then you've got your z-score sheet. So if you look at your z-score sheet, go to the second page where it's the positive z-scores and look at the bottom right. The bottom right has a little table that has something that says confidence. I need to change the color. Confidence level. It says confidence level. And then critical value. And it gives the confidence levels. So, for example, ours is 90%. So I'd put 0.9. And the number that goes with it is 1.645. So it finds these values for you. So you don't have to look and find the z-score every single time. You just have to use this chart, and it can give it to you because it's the exact same number that we would have found in our z-score chart the long way, technically. So use this. If you don't know, if you can't find it, please reach out to me because this is a tool that will make your life a lot easier because that's really the hardest part. All right, so that's step 3. My z of alpha divided by 2 is 1.645. All this is my critical value. That's the same thing. If you see the word critical value, that's all it means. That's what we just found. And so, again, that's one of the hardest things. Okay, so step 4, I'm going to erase that, is actually creating the confidence interval. The confidence interval is p hat plus or minus z of alpha divided by 2 times the square root of, make my square root a little bigger, p hat times 1 minus p hat divided by n. Sometimes in your formula sheet, this will say P. If you have a population, use it, but most of the time we don't have one, so we just use P hat. Okay, so 0.6298 And we said that that was 1.645. So now we're just plugging in. 0.6298 plus or minus. That z of alpha divided by 2 was 1.645 times square root of 0.6298 times 1 minus 0.6298 all divided by n, which was the total amount of people that we asked. Don't confuse n with this number of people who are in favor. N is the total amount of people that we asked. Alright, I'm going to put this second half in my calculator first. When I put that in my calculator, so I get 0.6298 plus or minus 0.1088. 0188. And you're almost done. So I'm going to erase everything but this. So pause it if you need it. Okay. 0.6298 plus or minus 0.10188. So to find our confidence interval, I've got to do two different operations. I've got to do this 0.62 minus all that, and then this 0.62 plus all that. And so I'm going to write it out this first time. 0.6298 minus, because the smaller one's going to go first, comma, 0.6298 plus. Once I simplify those, I get 0.6110, comma, 0.6486. That is my confidence interval. So it's being based on this proportion, plus or minus the margin of error, that give or take. So I know that basically I can be confident that 90% of the time I will get an answer anywhere from 0.6110 to 0.6486. Let's say I asked another 2,000 people and I did this again. I could expect it to be somewhere between this interval. It's also the same as 61.1% to 64.86% of the people. I can expect 90% of the time for them to be in favor of the death penalty within this proportion. So that's pretty cool. So that was step 4, to actually find the confidence interval. And step 5 is to do something that's called interpreting it. And to interpret it, we always pretty much do the same thing. So I'm going to talk about that next. Okay, so I'm going to kind of lay it out. So we always say, we are, or I am, blank % confident the true population blank of whatever we're talking about. So we're talking about of voters in favor of the death penalty is between blank. So we basically can fill in these blanks with the percent of confidence could be different. So in our case, it was 90%. Could be 95, could be 80. whatever it says. Of the true population, we're talking about proportion. Sometimes it'll be mean. That's what we're going to talk about in the next section. And of course, voters in favor of the death penalty, that's just whatever it is that you're talking about. If we were talking about of people who liked dogs, then that's what we'd put there. Is between, and then you put your confidence interval. So we got is between 0.6110 to 0.6486. And then you are done. So you can also use a formula to find out how much of a sample size you need to get some sort of error, a specific error. And you can just use this formula, which I would write down. And again, it's just kind of plugging it into that formula, and now we're just solving for n. So we could have two possible solutions. We could use an estimate of p hat based on a number that we're given. So like our p hat earlier was 0.6298, I think. If you're not given a p hat, you can just use 0.05, but I will say most of the time you're given a p hat. And this should look like that. Sorry, I don't know why it cut it off. But basically, technically, if you're not given a p hat, a good estimate is to say p hat's just in the middle, which is 0.5 or 50%. So again, this is the formula that we're going to use when we have a p hat that we know, because we just plug in the p hat for these values, or for these variables. And then, so again, this is something that you're going to want to write down, this formula. If you don't know p hat, then you can use this formula, which is, remember, if we don't know p hat, like I said, we just assume it's 0.5. So if you were to plug in earlier, p hat times 1 minus p hat, if we were to plug in 0.5 for each of those, you would get that 0.25. So that they're basically just giving you a simplified formula. Once again, you really don't use this one a lot. You can use this one down, write this one down if you want, but if you think it might confuse you, then just don't write it down, and just know that if p hat isn't given to you, then use 0.5. Alright, so we're going to use this formula. We want to determine a sample size. A sociologist wanted to determine the percentage of residents of America that only speak English at home. What sample size should be obtained if she wishes her estimate to be within 3 percentage points with 90% confidence, assuming she uses the estimate obtained from the Census 2000 supplementary survey of 82.4. Okay, so we know that we're going to be using this new formula when it says what sample size should be obtained. Like we're looking for n. We don't know n. And that formula is p hat times 1 minus p hat times z alpha divided by 2 over e squared. So first off, we've seen most of these except e, which we have still seen. That's just your error. So let's just go through here really quick and figure out what we know. So if I'm given a percentage or a part out of a whole, that's going to be my p hat. And I'm given that 82.4. 82.4 as a decimal is 0.824. My e, anytime it says within something, that's going to be your margin of error, that give or take. So within 3 percentage points, it's going to be your error. And it's basically saying 3%. So 3% as a decimal is 0.03. And then I need to find my z of alpha divided by 2. That's just my critical value, basically. You can honestly just think of it like that. And that's when we're going to look at that little cheat sheet on the bottom right-hand corner of your z-score sheet, the positive z-score. And it's a 90% confidence. So you're going to go to that one where it's confidence level, critical value, 0.90. And the number that goes with that is 1.645. And so we're going to plug that in. Z of alpha divided by 2 is 1.645. And now we've got everything we need to plug into this formula. So n is equal to 0.824, 1 minus 0.824 times z of alpha divided by 2, that was 1.645, divided by e, 0.03 squared. Plug this in your calculator. I should get 436.04. You always round up. I know that's weird because it's 0.04 and you want to round down, but you always want to overestimate sample size. So it's actually 437. So basically you need to ask 437 people if you want to have a margin of error of 3%. And so it's just finding how many should I sample if I want this. 9.2 is estimating a population mean. So in order to do that, we're going to obtain a point estimate for population mean. State the properties of the t-distribution. Determine t-values. Construct and interpret a confidence interval for population mean, and then determine the sample size for population mean. Okay, this may seem like we've already done it because we kind of have, but we did it with population proportion, and now we're talking about population mean. And so remember, mean is just average. And we're going to do the same thing that we did with proportion, but with mean. And remember that X bar is the sample mean and mu is the population proportion, and X bar is a good estimator of the population mean. And so X bar is our point estimate that's going to estimate our parameter mu. So let's do a little recap on how we actually find X bar. So computing a point estimate. Pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. The following data represent the weights in grams of 17 randomly selected pennies minted after 1982. So here's all their weights. Treat the data as a simple random sample. Estimate the population mean. Okay, so we have a sample. Remember to find the mean of a sample. We add all the values up and divide by however many there are. So if I added all of these, the weight of these pennies, and divided by 17, because that's my n, so add them all up, divide by n, I get 2.464 grams. Okay, let's remember population standard deviation. We're not going to do it, I promise. And this slide's messed up, but just remember the formula. For the formula, we needed mu, but we don't know mu. And if we don't know mu, then we also don't know sigma, right? We need mu to find sigma. So if we don't know mu, we don't know the standard deviation. Now remember, if mu and sigma are unknown, then we can standardize x bar as this. This is the formula that we went over in Chapter 8. So this is the standard version of x bar. And x bar is a normal distribution. And if it's a normal distribution, then we can use z. So I'm going to write the word normal. If it's normal, we can use this just like we learned in Chapter 8. So we can use that, but still, what if our sigma is unknown? And again, I think this is the last weird slide that's formatted weird. If sigma is unknown, then we have to estimate sigma with S. Remember that S is the sample standard deviation. So now we're approximating the mean and the standard deviation when we use our confidence intervals. So normally we use z equals x bar minus mu of sigma divided by root n. But if we don't know this, then we have to use a new formula. So this will become a new formula, which is in your formula sheet. And it is T equals, and it's on the next slide as well, x bar minus mu of S divided by root n. So I'm replacing sigma with S. And this is called the studentized version of x bar. It follows a normal distribution, at least approximately. Then T follows the student T's distribution. If our sigma is unknown, that's when we use this T. And when we use this T, it also follows something called DF, which is degrees of freedom. And DF, how you find degrees of freedom, is just n minus 1. So our sample size minus 1. Suppose a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of, so that's your new formula, follows student T's distribution with n minus 1 degrees of freedom, where x bar is the sample mean and S is the standard deviation. So this is what we're going to use now if it's not, if we're not given sigma, and we only use T when we're talking about mean. You can now use T when you're talking about mean, but still Z for proportion. So I know that's kind of weird, so let it sink in for a little bit before you move on. And I'll show you some examples as well. Okay, so let's compare standard normal distributions to the T distribution. So let's say we had 1,000 simple random samples of size n equals 5 from a normal population. Let's say our mean is 50 and our sigma is 10. Determine the sample mean and sample standard deviation for each of the samples. So I drew a histogram on the next page with a simulation, so we're going to look at it. I think it cut a little bit of it off, but I'll give you an idea of what it looks like. Again, I apologize, I have no clue why it does this, but it's pretty normal. Approximately normal for the Z. So this is if we were to use our Z-score. If you want to know what it looks like, you could look on the PowerPoint since it cut that off a little bit. And then T looks like this. It's not as tall as Z, and it's a little more spread out. It's got this randomness. So the histogram for Z is symmetric and bell-shaped, with the center of the distribution at 0, and pretty much all of the rectangles are between -3 and 3. So Z follows a standard normal distribution. And the histogram for T is also symmetric and bell-shaped, with the center at 0, but the T is more spread out. It has longer tails, and it's unlikely that T follows the standard normal distribution. The extra spread, in addition, in the distribution of T can be attributed to the fact that we use S to find T instead of sigma. So we use the sample standard deviation instead of the population standard deviation to find T. Because the sample standard deviation is itself a random variable, we have more dispersion when we use T instead of Z. Couple properties of T. T distribution is different for different degrees of freedom. It's centered at 0 and symmetric about 0. The area is still 1. As T increases or decreases without bound, the graph approaches 0. The area in the tails of the T distribution is a little greater than the areas of the tails of the standard normal distribution. Whenever you see standard normal, it's just talking about your Z. Because we are using S as an estimate of sigma, thereby introducing further variability into the T statistic. And again, like anything else, as sample size increases, we get closer to the normal, standard normal density curve. So the more sample size you get, the better idea you get of what the actual population is by law of large numbers. And here's a visual. Let's assume that this blue line is what the normal curve looks like. It's skinnier and taller, less dispersion. And you can see that this orange one is the shortest and the more spread out. And then as you increase the size, it gets closer to what the normal looks like. Normal being your Z. And so as you increase sample size, T will eventually look like Z. All right. Should look like that. And this should be T sub alpha. The notation T sub alpha is the T value such that the area under the standard normal curve to the right is alpha. So, whenever you look this up in your chart, and I'll teach you how, it is going to give you the area to the right. Z-score gives you area to the left. T gives you area to the right. Alright, so how do we find the T value? So first off, if you go to, again, it is course information, course resources under modules, and click on the Z-score sheet. It is the third page, and it says table A-3, T distribution. So it's kind of similar to your Z-scores, except degrees of freedom go this way, and then the area goes this way. And so it says, find the T value such that the area under the T distribution to the right of the T value is, I'm going to change that to 0.01. 0.01, assuming that the degrees of freedom equals 10. So we're really finding T of 0.01 with the degrees of freedom of 10. And so what you're going to do is you're going to find the degrees of freedom of 10. And we're only finding the area to the right, which means that it's considered one tail. So you'll see two different things, area in one tail, area in two tails. You need to be in the area of one tail and find that 0.01 and then see where they meet. And where they meet is that critical value, the t value, that we're trying to find. And let's see, 0.0110, that should be 2.764. And that's your t value. So t value to the left of to the right of 0.01 with a degrees of freedom of 10, 2.764. Okay, so let's find confidence interval for mean. So our assumptions are that n is greater than or equal to 30. You have to check that. For p, it's that p times 1 minus p needs to be greater than 10, or n times p times 1 minus p. This one you just have to see if n is greater than 30, and if it is, you're good to go. Steps to find confidence interval. This is on your PowerPoint, but for some reason it's formatting it weird. So we need to find alpha or find the confidence level depending on whatever it gives us by doing 1 minus alpha or 1 minus the confidence interval. Solve for alpha. And then find alpha divided by 2 because it's going to be two-tailed. We're going to find degrees of freedom. We were given degrees of freedom earlier, but if we're not given degrees of freedom, it's n minus 1. And then you need to find t. Oops. Did it again. For alpha divided by 2. Then we're going to find the confidence interval, which is the point estimate, x bar, plus or minus the margin of error, which is t alpha divided by 2 times the standard deviation, s divided by root n. And the last step is to interpret. Interpret. Sorry. Ran out of room. But those are your steps that we're going to follow when we're asked to find confidence interval. So we're not going to actually do a confidence interval first. I'm going to use a simulation to show you kind of what I mean when I say 95% and 90% confidence intervals, or whatever it is that we're using. So we'll use a simulation to obtain 30 simple random samples of size n equals 8 from a population that's normally distributed with a mean of 50 and a standard deviation of 10. Construct a 95% confidence interval for each sample. How many samples resulted in intervals that contain 50? So let's just say theoretically we did a confidence interval 30 times, and we want to see how many actually contain the real population parameter, the real population mean of 50. So here it is. Let's say these are all confidence intervals. And the bolded ones are the ones that do not. So this does not contain 50. But all of these did. Like, we just took a simple random sample of whatever it is that we were talking about. And this one contained the real population mean. This one contained the real population mean. So on, so on, so on. And so far, only 1 out of 10 doesn't. So that's pretty good. All of these contained the population mean. And what I mean by that is somewhere between 43 and 57 is 50, right? Somewhere between 49 and 63 is 50. So on, so on. Because that's our population mean. We're seeing how many times it actually captured that. And then here's 10 more. And this one did not capture the population mean. but all the other ones did capture the population mean in this interval. So that means that 28 out of those 30 contain the population mean, or 93%, which is pretty close to our 95% confidence interval. So 93% of those 30 captured the true population mean. And so in general, we can say for 95% confidence, any sample mean that lies within 1.96 standard errors of the population will result in a confidence interval that contains the mean, which is really what a confidence interval is. Again, like I was saying, if we were to do 100 of these, we would assume that 95 would capture the true population mean, and that alpha, or that 5%, that left over, would not capture the population mean. Okay, now we're actually going to construct a 99% confidence interval. So we haven't done 99% confidence interval yet, but that's okay. So remember, the mean is 2.646. That's my x bar. And the sample standard deviation is 0.02. So if I'm given sample standard deviation, that means I'm going to use t. But anyways, remember that our first we need to see if it's normal. So does it say that it's normal anywhere? No. But let's pretend it does. Approximately normal. It says see the next slides for normality, and I'll explain those, but honestly, I won't give you anything like that on a test. I'll either make n greater than or equal to 30, and in this case it's not because it's 17, or I'll tell you it's approximately normal, and if it's approximately normal, you don't even have to worry about this. So let's pretend it says approximately normal, so we're good to go. And once we're good to go, we need to say, okay, I know my confidence level is 99%, so what's my alpha? 1 minus 0.99. So my alpha is 0.01. But remember, if it's a confidence interval, then my alpha is over here and over here. It's the leftover. So I need to find alpha divided by 2. 0.01 divided by 2 is 0.005. And now I need to find my t value. To find your t value, we need that. That's the area of my tail. And we also need my degrees of freedom. Degrees of freedom is n minus 1. My sample size minus 1. And my sample size here was 17, I believe. 2, 4, 6, 8, 10. Yes, 17. So 17 minus 1, my degrees of freedom is 16. So go to your t-chart. And once you're at your t-chart, you will see, again, area in one tail or area in two tails. If we divided that by 2, this 0.005 is just the area of one tail. So you're going to use that. And then 16 degrees of freedom, and figure out where those numbers meet on that chart. And the number where they meet is 2.921. That's your t value. So I'm going to go ahead and erase this so I can construct my confidence interval. Pause it if you need to. So 2.921. So to find confidence interval for a mean, it's x bar plus or minus t of alpha divided by 2 times s divided by root n. So my x bar was that 2.464 plus or minus that t value is that number that I just found when I looked at my t chart, and I got 2.921 times the standard deviation, which we were given, divided by the square root of n, which is how many samples we took, 17. You can find that by counting those, or sometimes it'll just tell you n equals 17. Okay, 2.464 plus or minus, if I multiply these together, I'm going to end up getting 0.0142. All right, so I'm going to go ahead and erase this again so I can show you how I'm going to get this confidence interval. 2.464 plus or minus 0.0142. So the first one I'm going to subtract because that's going to be the smaller number, comma, then I'm going to do the same thing, but I'm going to add. When I add and subtract those values, for the first I'll get 2.4498. And for the second I'll get 2.4782. And that is my confidence interval. And that is step 4. And the last step is we have to interpret it. So again, we're going to use that kind of blanket statement. We are blank % confident the true population mean of whatever we're talking about, pennies minted, after 1982 is between, we were talking about the mean weight of pennies minted after 1982 is between, and then you put your answer. So we were 99% confident that the true population mean weight of pennies minted after 1982 is between that 2.4498 to, sorry I'm running out of room, 2.4782. And that is your confidence interval about a population mean. This is just showing you that it was normal. This is like the 7-3 stuff where it uses technology to see if it's normal. Again, I'll just tell you if it doesn't meet the requirements of the sample size, I'll just tell you it's normally distributed so you don't really have to worry about. And here's a box plot of the data just to show you there's nothing crazy going on. Okay, we can also determine the sample size using a population mean. And so we are going to use this formula. This time you are going to use Z. And it's n equals Z of alpha divided by 2 times S divided by E squared. N is rounded up always to the nearest whole number. Determine the sample size. So go back to the pennies. How large a sample would be required to estimate? So how large a sample? We're looking for N. To estimate the mean weight of a penny manufactured after 1982 within 0.005 grams with a 99% confidence, assume S is equal to 0.02. So let's write down that formula really quick. It is N is equal to Z alpha divided by 2 times S divided by E squared. So our S is 0.02. Anytime you're given something that says within, that's a margin of error. So 0.005 is E. So we just need to find Z of alpha divided by 2. we can go to our z-score chart and just look it up in that bottom right-hand corner, the critical value, and we have a 99% confidence, so the one that goes with 0.99, the critical value that goes with 0.99 is 2.575. So that's whoops, I wrote that completely opposite. 575, sorry. And that's the hardest part, honestly, is finding that z-score, because once you've got that, you can just plug everything in. So 2.575 times S divided by E. Put that in your calculator. 2.575 times 0.02 divided by 0.005. Square that. Got a very large number. Got a very large number. I'm going to check my calculations really quick. Oh, I added it. That's why. Let's do that again. Sorry. 2.575 times 0.02 divided by 0.005. That looks better. Okay. When I divide these in my calculator, I get 10.3. Still need to square that. I get 106.09. I know you're tempted to round down, but you always round up. So it's 107. Whoops. Sorry. I do not know why I did that. You might want to go back on that, but anyways, we get 107 for our sample size.